All right, so we're going to finish out chapter 13. This is the second part. And we're going to pick up with colligative properties. And in a colligative property, these are things that depend on how much is added, not what is added. So it doesn't matter if we are adding, for example, KCl or NaCl. It only depends on how much, not what it is we add. And the colligative properties that we're going to look at are vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. This would be an increase. So if you'll notice, there's two of them that go up, and then there's going to be two of them that go down. All right, so we're first going to look at vapor pressure. And remember, the vapor pressure is the pressure of the vapor exerting a force on that liquid. So it's the pressure of the vapor, the gas part, pushing down on it. And it's proportional to the concentration. And we're going to be measuring that concentration in mole fraction. And if we add a solute, it lowers the vapor pressure, because if there is, for example, salt water, the salt is going to kind of keep that water from evaporating, so there's not going to be as much vapor, therefore not as much vapor pressure. And Raoult's law is the law that we use to describe this behavior. And the pressure of the solution, that means the solute and the solvent together, that solution, is equal to the mole fraction of the solvent times the partial pressure of the solvent. Now this is usually where things kind of go awry when we solve a problem. A lot of times we're doing the mole fraction of the solute, like what it is we're putting it into. But for Raoult's law, we need to use the solvent. So if we're adding salt to water, we would be using the water part. And if it's called an ideal solution, if they mention that in your problem, that means that it follows Raoult's law. All right, so glycerin is a non-volatile electrolyte, non-electrolyte, and this is important. If it's an electrolyte, we would have to put in another factor, and we will be looking at that in later problems. And non-volatile means it doesn't evaporate. So those two things tell me that this is going to be an ideal solution, so we're going to use Raoult's law. And then it gives me the density and the temperature, and it says calculate the vapor pressure with 50 milliliters of glycerin in 500 milliliters of water. And the vapor pressure of water is 23.8 torr, and it gives me the density of water. So we're going to have to find the mole fraction. So that means I need to find the moles of the glycerin. So I take the volume times the density in order to get the mass in grams, divide by the molar mass to get me the moles of glycerin. Then I'm going to do the same with the water. I'm going to use the volume and the density to get me the mass of the water, divide by the molar mass to get the moles of the water. Now, to calculate the mole fraction of the water, I'm going to put the water over the total. And that gets me a mole fraction of 0.976. And then to find the pressure of my solution, I'm going to take the mole fraction that I just calculated times the pressure of just the water, which is this 23.8. And that gets me 23.2. And notice this pressure is less than what we started with. So anytime I add something to my solvent, it lowers that vapor pressure. All right, the next colligative property is boiling point elevation. And since it says elevation, the boiling points of solutions are higher than the boiling point of the pure solvent. So let's say we're driving through the desert and we have water in the radiator of our car. If we have antifreeze in that water, then what that means is it's not going to boil at the normal boiling point. It's going to boil at a higher temperature. So that means it can get much higher before it's going to boil. Well, that's good. If we're driving through the desert, we don't want the car to overheat. So we want that water to be able to boil at a higher temperature, not the normal boiling point. Now, for freezing point, this is the opposite. For freezing points, when we add something to water, it lowers the freezing point. So the example here is if I put salt on an icy road, then instead of the water freezing at 0 degrees Celsius, it's going to have to get much colder before it would freeze. Another example is a lot of times if you're making homemade ice cream, the ice cream mix on the outside of that container that you have the mix in, on the outside is usually salt water. And that's because water has a freezing point of 0, but salt water would have a freezing point that is lower than that. That allows it to be even colder, helping to harden that ice cream. All right, now the nice thing is the equation is pretty much the same. If you want to find the change in boiling or the change in freezing, you take I times K times M. Okay, so I is called the Van't Hoff factor. And if you have an ionic substance, the I tells me the number of ions. So for NaCl, Na is 1, Cl is another one, so it'd have an I factor of 2. If we had Na2 SO4, for example, Na2 means 2 NAs, 1 SO4, so the I factor would be 3. So if it's ionic, you're going to have to put an I factor in there. And it's not going to tell you it's ionic, you just have to know that it's ionic, meaning metal with non-metal or contains a polyatomic ion. Then Kf or Kb, these are the mole boiling and freezing point constants. Those would be given to you in a problem. There's a table that's in your textbook that looks like the one on this slide where they're going to give you Kf and Kb. Also on this chart are the normal boiling and freezing points. Now we know what those are for water, but if I was putting this as something like chloroform, I wouldn't know what the normal boiling and freezing points are. So that's why they're given. And then M is the molality. And in the previous video, we had a video on how to calculate, or a problem on how to calculate molality. Now, the change is going to be what it is for the solution minus what it is for the pure solvent. Okay? And for the change in freezing, actually this has, yes, for the change in freezing, it would be the solution minus solvent. Notice this one is a negative because the freezing point gets lower. So whatever that change is, you add it to the normal boiling point for boiling, or if it's freezing, you subtract it from the normal freezing point. All right, so in this case, they want me to calculate the new boiling point of a solution, an aqueous solution, meaning it's in water, that's 25% ethylene glycol by mass. So I got to go back to my how to find percent by mass. So molality, remember, is moles over kilograms. So if I have a 25% mass solution, that means there is 25 of the ethylene glycol over 100 total, and then I would multiply by 100. So I'm going to take 25, and now we've changed it times 10 to be 250. And then if I have 100 total, 100 minus 25 would be 75 of the water. Okay? And then if this is my ethylene glycol, I'm going to divide by the molar mass. That's going to get me the moles of the ethylene glycol. And then this is my grams of water. If I change it to kilograms, then I have moles of the ethylene glycol over kilograms of water. That's going to get me my molality. Okay, now my change in boiling point is I times Kb times molality. That should be a lowercase m. So 1 times 0.51 times 5.37, and I get 2.7 degrees. That tells me that the boiling point is going to be raised by 2.7 degrees because that's my change. So water normally boils at 100. I add the 2.7, making my new boiling point 102.7 degrees Celsius. Okay, last one is on osmotic pressure. So a semi-permeable membrane is a membrane, kind of like a filter if you want to think about it, that allows certain things to go through. They allow smaller particles to go through, but larger molecules will not. And osmosis is the movement of solvent molecules from a solution of a low concentration to a high concentration of solute across the membrane. All right, and the osmotic pressure is the pressure that's required to stop osmosis. So imagine that you would have a brick wall, and in a brick wall, you've got parts where there's mortar. So let's say you've got places where the mortar is coming out, and so water, which is the solvent, starts coming in to your brick wall. So let's say where there's a little piece of water coming in, you try to plug it with your finger. So you put your finger there and you're going to plug one of the holes. Well, let's say another hole enters up, so then you plug that one. So you keep having to plug all these holes. So imagine instead of having to plug them with your fingers, if you could just push with an amount of pressure that it would keep all that water from coming through. It would stop the osmosis. And that is the osmotic pressure. That's the amount of pressure that we would have to exert to stop the osmosis. Now, if you've ever heard of an RO or a reverse osmosis system, that's in order to purify drinking water. What happens there is a reverse osmosis runs osmosis in reverse. So not only do we overcome that osmotic pressure, but we apply even more pressure to reverse the flow of osmosis. So in that case, we're going from a high concentration of solute to a low concentration of solute. And remember, the solutes is stuff being dissolved. So let's say I have a large amount of iron in my water and I have an RO system. The water then would flow from the high amount of iron, which would be the tap water, into a low amount of iron in there. And that would be the purified water. Okay. Okay, so I think, all right, so when we talk about osmosis, we have solutions that are isotonic. In that case, they have the same osmotic pressure as what they are in. That means the solvent passes the membrane at the same way, both directions, which means it's kind of a wash. Now, there's the same amount going one way as there is the other way. In a hypotonic solution, we have a lower osmotic pressure, which means the solvent is going to leave this solution. Some is still going to be coming in, but I have more of it leaving. And in a hypertonic, hyper meaning, think about a hyper kid, too much energy. In this case, we have too much concentration. So we have a higher concentration, which means a higher osmotic pressure. That means the solvent is going to come into this solution at a higher rate than it leaves. So with hypo, that means water or whatever the solvent is leaving. In hyper, it's coming in. All right, so for red blood cells, they are semi-permeable membranes. So if they are in a hypotonic solution, and remember, water is going to be entering the cell in a hypotonic solution, they are going to grow until they burst because all the water is coming into the cell. And when it bursts, this process is called hemolysis. Now, if it's stored in a hypertonic solution, and when we say stored in, so imagine your bloodstream. You are a big giant solution. Let's just pretend it's only salt water. You have a lot of other ions dissolved, but pretend it's just salt water. Your red blood cells are in your bloodstream, right? So let's say that the concentration of salt is going to be lower in the cell than it is or lower on the outside than what it is on the inside. So in that case, the water is going to come into the cell. Now, if it's in a hypertonic solution where there's a higher concentration, then that means water is going to leave the cell. As water leaves the cell, it's going to cause the cell to shrivel, and this process is crenation. So if you would go into the hospital and you are dehydrated, we want to make sure, or even if you're not dehydrated, but a lot of times when you're dehydrated, they'll start an IV solution. But anytime you're going to be in an IV situation, you want to make sure that those solutions are isotonic to blood. Meaning I don't want to have hemolysis or crenation. I don't want to go in there and get more dehydrated, nor do I want my cells to be bursting. So I want to make sure that the concentration in and out of the cell are the same. All right, so this is a problem on osmotic pressure. Osmotic pressure is pi, and that equals IMRT. I is still that Van 't Hoff factor. So if this solution is ionic with a solute, I'll need to put the number of ions. M is the molarity, capital M. R is our same ideal gas law constant, 0.0821. And T is going to have to be our temperature in Kelvin. Okay, so if I just rearrange my equation, M is going to be pi divided by IRT. All right, so 7.7 is my osmotic pressure. 25 is my temperature. I'm going to put it in Kelvin. Glucose, they gave me the formula several slides ago. Glucose is not ionic, so that means it's just 1. Or you could leave off the 1 if you wanted to. And then R is our 0.0821. So we find that we get an osmotic pressure of, or molarity of 0.31 molar. All right, the last part of this chapter is on colloids. And colloids are things that aren't solutions where they're all homogeneous and you can see through them. Suspensions are things that the particles, the solute particles, are so big that they settle to the bottom, like muddy water if you let it sit. Or if you think about your ketchup, how the water always settles out from the stuff and you got to kind of shake it up, or your vinaigrette dressing, those are suspensions. A colloid, the particles are small enough that they stay suspended in the solvent, but I can't just see through them because a solution, the particles are so small, I can't even distinguish them. In a colloid, I actually see those. An example of that would be like milk. Okay, I don't have to shake my milk up, unless of course you're getting it straight from the cow, but like when you get your milk, I don't have to shake up my milk at all. It all stays suspended throughout. In this case, this is just kind of a chart that's showing different kinds of colloids and what the solvent and the solute are like. So for example, if we're talking about fog, this is an example of an aerosol type of colloid. And in that case, we have liquid solute, which would be water vapor, the water molecules suspended in the air, which is the gas. If we talk about milk, that's an emulsion, and that is a liquid solute in a liquid solvent. Paint. Paint you always have to mix up. Let's see, marshmallows, butter. So they've given you several different examples and what the solute and the solvent phase are. Now we can tell if we have a colloid because a colloid is going to have the Tyndall effect. So in a solution, they do not scatter light. So if I shine light on it, nothing happens. So in this first one, you can see I shine light through it, nothing happens, it's just the solution still. In a colloid, what's going to happen is the light is going to be scattered. So right here, you can see when I shine light through it, all of a sudden now I can see that the light is being scattered. Another example is when you're driving and it's really foggy. The fog is going to scatter the light, making it very difficult for you to see because fog is going to be a colloid. Now we talk about biomolecules, and I'm going to kind of go back, way into chemistry when we talked about soaps, because this is where we first talked about hydrophobic and hydrophilic. So hydrophilic things are water-loving, while hydrophobic, phobic meaning fear of, they don't like water. So if they're hydrophilic, they're going to be polar. If they're hydrophobic, they're nonpolar because water is polar. So large molecules that form colloids in water have hydrophilic portions, so they're going to have both. They're going to have the hydrophilic portion facing outward to be around the water, and then the hydrophobic part is going to be facing inward. And we're going to get to our soap discussion here. Now, what happens in an emulsifying agent? And this picture should look very, very much like when we talked about soaps and soaps forming micelles. So let's say this is our blob of oil or grease. And this is my soap, which has both a hydrophobic part, the nonpolar tail, and the hydrophilic part, which was the ionic head. So in this case, you'll notice all the nonpolar parts are attracted to the oil and grease, and all of the hydrophilic parts, the ionic head there, is going to be on the outside toward the water. Now the same thing, if instead of talking about soaps, we were talking about other colloids, in this case in biological systems, it's the exact same way. So we're going to have the hydrophobic tail on the outside, the hydrophilic part on the outside to interact with the water part. And this is going to help in digestion by allowing passage through the cell wall.